Hi, this web lecture will be about the PN junction, about the diode, PN diode. I will intuitively explain the operation of the PN diode. So we'll start with a silicon semiconductor. Here is the silicon, it's drawn here. And we will have two parts. One will be a p-type and the other will be an n-type. The p-type is doped with acceptor atoms, which can be represented as an acceptor ion, negatively charged ion, immobile charge, and the mobile hole that it releases. The n-type semiconductor is, for example, the silicon, which is doped with donor ions, represented by a donor ion. This is immobile, and the electron that it releases, the mobile charge. So here with black we still have, of course, the silicon atoms. So we have here an n-type semiconductor where the majority of the carriers, mobile carriers, are the electrons. And here we have the p-type semiconductor where the majority of the carrier of information, the carrier of current, are the holes. So now the question is, what happens when we connect the p-type region with the n-type region? So the first thing that will happen is that the electrons here will try to move to this side. And the reason is that here in the n-type the concentration of electrons is huge, in the order of 10 to the power of 16 electrons per cubic centimeter, while the electrons here, they are just a few minority carriers, and their concentration is very, very low, for example in the order of 10 to power of 5 electrons per cubic centimeter. So there will be a diffusion force which will drive the electrons from the n-type to the p-type. So for example this electron, we want to move here where the concentration in the p-type of electrons is low. The same, of course, will happen with the holes. The concentration of holes in the p-type is very, very large, and the concentration of holes in the a-type is very, very low. So the holes will try to move to this side. As electrons move from this side to that side, they will perhaps recombine with holes and they will annihilate each other. So this will happen with this. For example, this electron will move here, recombine with the hole. Some holes will recombine from here, here. Yeah. Let's do this also for these 4 electrons, which move here, and these holes will move here, will recombine and annihilate with the other electrons here. So let's stop for a while. So what happened as the mobile charges, for example the holes, move from the p-type to the n-type through diffusion, they leave behind the immobile, negatively charged acceptor ions. So they are locked in the crystal, the silicon crystal, they cannot move the ions. So a net negative charge remains here. The similar thing happens in the p-type semiconductor. As the electrons diffuse in this side, they leave behind the positively charged donor ions. So there will be actually from here to here an electric field created, because here we have positive charge, which are clearly separated by this barrier. This is the metallurgical junction, the metallurgical border between the N-type and the P-type, the metallurgical junction. Here we will have positively charged ions, and here we will have the negatively charged ions. So this will create an electric field starting from here and finishing somewhere here. Now, the electric field will basically exercise a drift force on the electrons in this direction and for the holes in that direction. So this force, drift force, will be the opposite force of the diffusion, and it will balance the diffusion force. So this migration that we described in the beginning, due to diffusion of electrons from N region to the P region, will be stopped actually by the created electric field. So the diffusion will stop, for example, in a region which is like this. For the electrons, from going from here to here, there will be diffusion force. But for the electrons from here to here, there will be a drift force. So the drift is due to this built-in electric field. For the holes, it is exactly the opposite. There will be the diffusion force from this side to this side. So this is diffusion electron, and this will be drift electron. And for the holes, there will be diffusion force in this direction. Diffusion for the holes. But there will be a drift force due to this electric field in this direction. The diffusion and the drift current, the diffusion and the drift forces will create basically currents, because we have moving of mobile charges. So there will be four types of current: diffusion and drift current for the holes, and diffusion and drift current for the electrons. So if we try to from this side to this side, we will have the diffusion current for the electrons. Electrons want to go from areas of high concentration to areas with low concentration, but due to this electric field, there will be a drift current for the electrons. The same with the holes. From this side, area with high concentration of holes, to area of low concentration of holes, we will have diffusion of holes. And due to this created electric field, from this side to this side, we will have drift of holes. as we have no externally applied field, this p-n junction will come into thermal equilibrium. This means that it will come to a point when these currents, the diffusion and the drift currents, balance each other and there is no net current. So the current will be zero because the diffusion and the drift currents will balance perfectly. The region that is created here through the electric field is effectively void, empty of mobile carriers. As you can see, we have only ion charges, positive and negative ion charges, but we have no mobile charges. There are no holes and no electrons in this region. We call this region depletion region because it is depleted from mobile carriers. So let's see now what will happen if we apply an external voltage across the p-n junction so that we can build the volt-ampere characteristic of a diode. So imagine that we have here an external voltage. We connect the positive side of this external voltage to the p-type and the negative side to the n-type. First of all, we will investigate the point when this voltage is zero. So the voltage is zero, the external voltage that we apply is zero. As we discussed before, the diffusion and the drift current will perfectly balance each other, resulting in no net current. Now, let's investigate what will happen if we have actually a negative voltage applied here. So we'll have negative voltage. Then here we will apply low potential, here we will apply low potential, here we will apply positive potential. So the external field actually is in this direction from here to here. It is in the same direction as the internal electric field which was created due to the positive and the negative ions. So the new electric field that we will apply is in the same direction. Therefore, the total electric field that will be on the p-n junction will be increased by the externally applied electric field from here to here. So this electric field will actually increase the depletion region. Will increase the depletion region by basically depleting more mobile carriers. So if we apply external electric field which is in the same direction as the internal electric field of the p-n junction, the depletion region will have to increase in order to accommodate the total electric field, the external plus the internal. So the new area for the depletion region will be actually this one. Now what we see is that we actually tolerate the drift currents, and we make it even harder for electrons to diffuse from the n-type to the p-type. now it's harder because the electric field that they have to oppose is larger. So there will be exponentially less electrons that can make it across the depletion region. Hence, the diffusion currents will decrease. What will happen with the drift current? To understand what happens with the drift current, we have to first look at how this current is generated. Inside the depletion region, we still have the silicon atoms. Due to thermal generation, we can create still inside pairs of holes and electrons. If such pairs are created, they will be swept by the electric field. So this hole will come here and this electron will come here, and this is how the drift current actually is generated. So you can see that the drift current depends only on the thermal generation of whole electron pair and not on the size of the depletion region or the size of the electric field. So the drift current will essentially remain the same, while the diffusion current will decrease exponentially to a negligible value. So the total current will actually decrease and eventually saturate to the drift current only, which is due to the thermal generation of whole electron pairs within the depletion region. This current we call the reverse diode current. Now let's see what will happen if we apply an external positive voltage. So
we'll return basically to the original depletion region. Let's return the holes here. Like this. And now we apply a positive external voltage. So
positive external voltage is here is plus and here is minus. So the external field will be of this direction. External field. So what we see is that the external field now opposes the internal field. Hence the total field, external plus internal electric field, will be reduced. This will reduce also the area of the depletion region. So the total of this, say it will be this size.
the total depletion region will have to reduce. Like this.
As the size of the depletion region reduced and the effective electric field is reduced, then there will be exponentially more electrons, so these are electrons, exponentially more electrons that will acquire the sufficient energy to diffuse from the N-type to the P-type. And there will be exponentially more holes, mobile carriers, that will acquire the sufficient energy to diffuse from the P-type to the N-type. What will happen with the drift current? It will stay the same, because the drift current depends on the thermal generation of holes electron pairs. So it will remain the same, the drift current will remain the same, while the diffusion current will increase exponentially. write like this explanation. And this is the intuitive explanation of the operation of PN junction. The important concepts that we have to remember are listed here. We have to distinguish between positive and negative charges. When we have equal amounts of positive and negative charges, we have electrical neutrality. We have to distinguish also between mobile and immobile charges. The immobile charges are the ions. They're locked in the crystal lattice and they cannot move. While the mobile charges, they are the holes and the electrons, they can move. And they can move due to two forces. The diffusion force, where they move from areas with high concentration, for example the electrons from here to here, to areas with low concentration of electrons, to use this example. And the drift force, where there is electric field and this electric field exercises a drift force on the electrons and the holes. The other concept that we have to distinguish is the thermally generated mobile charges, electrons and holes, and the mobile charges which are due to doping. The thermally generated charges are responsible for the drift currents, mainly, while the charges due to doping are mainly responsible for the diffusion currents. Thank you very much.